Okay, so now we need to find the expression for energy of the orbits. So whenever we talk about energy, we are talking mechanical energy. That is, we need to find one kinetic energy and two potential energy. So at first let us uh, do kinetic energy. Now, here's an interesting fact I want to tell you, that as you saw that in case of Rn, it was quite a big expression to remember. Now, I don't know the expression for kinetic energy right now. If you tell me to write it down in the first line, I simply cannot. So I'll have to derive the equation and hope that it comes good, because I don't memorize it. And I'll tell you how we can also do it without memorizing and be sure that it's right. Let's do it. So you know the formula for kinetic energy is given by half mv square. And now we shall replace Vn using that one, Bohr's quantization rule, that is mvn Rn equals to, the same thing we'll be doing here as we did earlier as well. So let's put it, n square h square 4 pi square m square Rn square. Yeah. Now, as I said, you need to memorize the expression for Rn. This is why Rn is n square h square epsilon naught pi m z e square. Yeah. So put this thing here. Now this thing is squared, so don't get confused. Epsilon naught square. Now pi square m square z square e to the power 4. Now just relax and get this thing down slowly. Anything else? Yeah, this one. Okay, I don't think anything is left. Yeah, it looks pretty cool, kind of messy, but let's get it down. Let's see, we have m and z square e to the power 4, and down we have 8, and here n square h square epsilon naught square. So this is the expression for kinetic energy. Now as I said, I don't remember the formula, this one, so I don't know whether this is right or wrong, and same will happen with you when you try to derive it. So how to know if this is right or wrong? Simply we have to first calculate potential energy. So let's do it first, then we'll talk. So in this case we are talking about electric potential energy. Now in the first chapter we learnt about the electric potential energy. The formula was U equals to 1 by 4 pi epsilon naught Q1 Q2 by R. This was the formula. Now in this case we have a nucleus which has a charge of positive Za because it has protons, and we have an electron which has a charge negative E. So now if we put these values here, we'll get negative Z E square, and in place of R we should write Rn. Okay, so it was this easy. Okay, Q1 is this one and Q2 is this one. So that's it. Now simply put the value of Rn that I wrote. I think you should be memorizing that by now. It was n square h square epsilon naught pi m z e square. Yeah, say it a few more times and you will simply memorize, no problems. So let's see this one, and I don't think anything. Yeah, so that's all. We have m z square e to the power 4, and down here we have 4 n square h square epsilon naught square, and there is a negative. So this is the required expression for un, because this thing also is quantized, that is dependent on n. Yeah, so now as I said, I still don't know if I have gotten this expression right or wrong, but I have with me the expression for kinetic energy. Now both kinetic and potential, both are energies, so it should have same dimensions. So apart from this number, that is 4 and 8, the other things should be same. Simply compare the powers of each, and as I can see, these two are equal. Okay, so we can say that both are right, because if it was not equal, you have to then know that either this is wrong or that this is wrong, or even both is wrong. So you have to calculate it from the very first. So let's hope that doesn't happen. Practice it once or twice, you will get it simply. Okay, now look at one thing carefully. This thing and this thing are pretty similar, except for this fact there is 8 and there is 4. So if I simply multiply this kinetic energy by 2, and also there is a negative, we will get potential energy. So I can summarize it. Let's write it here somewhere, that potential energy is double of kinetic energy. By comparing you can see, and also there is a negative sign on potential energy. Potential energy is always negative, not positive. Okay, now to do the final thing, we need to get the expression for total energy, that is simply add this one and that one. Now see, apart from these two, 8 and 4, everything we have in common. So let me do that. In fact, I can take this as well. Yeah. Now we have this one is -1, this one is +1 by 2. So -1 plus half is -half. So the final expression for kinetic total energy should be m z e to the power z square e to the power 4, and there should be 8 n square h square epsilon naught whole square. This is it. Okay, and also sorry, -1 plus half is -half. So now again, as we can see, that the total energy is negative. Now compare these two, kinetic energy and total energy. These are exactly equal except for that negative sign. So we can write that total energy is equals to kinetic energy with a negative sign. And another thing, see, if we multiply this by 2, we will get the expression for potential energy. So we can memorize it, that potential energy is double of total energy, double of total energy, and both are negatives. Now this thing, the shortcut that I wrote or the summary, is very important and it's gonna be very helpful in some questions. I'll show you later. Okay, so we have the expression for total energy, and from here on we need to find the energy of hydrogen atom and some other atoms as well, and let's see, we'll take it from there. Okay, so now we have the expression for total energy here, from here. So just like we did for finding expression for radius, yeah. So for hydrogen atom, we have Z equals to 1, and for the first orbit we have N equals to 1. Put it in this one, we have the energy that is written as E1. We will be having 8 m e to the power 4 and negative 8 square epsilon naught square. Yeah, that's it. Now you need to memorize this value very carefully, not this expression but the value. If you put the values, you will get this negative 13.6 electron volt. Yeah, this thing is very important. You need to write it down in your head, minus 13.6 electron volt. Now again, let's find expression for the nth orbit, energy of the nth orbit. So as you can see, there is an n down, so let me write it like this. This n thing isolated will have n square into rest of it, negative into negative z, no, there is no z, sorry. We can write it like that. This is for hydrogen atom. Now everything apart from this n square is equal to E1, so you can memorize E1 by n square, this. Now again, if you need to find the energy for other atoms as well, you need to consider Z. So as we can see in this main equation, there is a Z square here. So we leave Z square and n square and the others for other atom. We have En equals to, there is Z square and down here is n square, and the rest are minus m e to the power 4 8 square epsilon naught square. Yeah, no, sorry, there is an 8. So again this thing is equals to E1, so we'll getting out of space here, En equals to Z square by n square E1. Now again, what you need to remember, not this one but this one, the value for first orbit, then relation for nth orbit of hydrogen atom, and for other atoms this one, Z square by n square. For Rn it was n square by Z. Now for energy it's Z square by n square. Try to memorize these things and we'll see, apply it some numerical problems and you will get it why these are so important. Okay, so let's now try to draw the energy levels of hydrogen atom, which will be very important in finding the spectrums as well. Now for hydrogen atom we need to be using this one, this. So let's write these all down. So we have the first energy, E1 is negative 13.6 electron volt. Now for E2 we have from this equation negative 13.6 by 4, so it will be negative 3.4 electron volt. Now for E3 we will have by 9, which is equals to 1.51 electron volt, obviously negative. And E4 is negative 13.6 by 16, which is negative 0.85 electron volt. And if we need more, by 25, and it should be negative 0.54 electron volt. As you can clearly see, I didn't use any calculator, or I didn't even calculate. Why? Because I simply memorized all these values. You don't need to memorize all the values going down to say number 6, 7 or 10 etc., but at least 4 up to level 4 please memorize, because these things will be very helpful in getting down the numerical problems, because you will not always have enough time, especially in the competitive exams. These values, memorizing these will help you big time, let me assure you that. Now let's plot them in a graph. Now see carefully that all the values are in negative, so our graph will be in the negative region. Now this graph will also be very important in drawing the spectrums. Now see that the first energy level is minus 13.6 and the others are less than that. Less than that means the magnitude is less, but these all things are negative, which means the first energy level is the least, it has the least energy, so it shall be down here, negative 13.6, its n equals to 1, energy level is negative 13.6 electron volt. Yeah. Now next one is minus 3.4. how to draw it? We see that this is 1/4 of the first energy level, so it should be, let's draw it in some estimated, this is half, this is 1/4, so it should be here. Yeah. Now the next one is minus 1.51. So it should be the half of this is here, which is 1.7. It is 1.1, so it will be a little further up here. And see one thing carefully, I am not measuring this by scale or anything, just estimated, and I am telling you how to do it, to estimate and still get it pretty much close to the actual scale. Now let's look at the next one, it is 0.85. now see, this is 1.5, so half of it would be here 0.75. this is 0.85, so it should be more than that, little downer, 0.75, so it should be somewhere near there. So it is, this place is quite crowded right now, you may not be able to see it. 0.85, this. Now if I can somehow squeeze in between this thing, the fifth energy level, which is 0.54, so the half of it is 4.3, a little more than that, half, yeah, here. So as you can see, this place has become quite crowded, and to draw it bare hands it's quite difficult. If you have the option, please use a scale, because things can get nasty here. 0.54 electron volt. Oh, this is crowded. Now look at this one thing carefully. The gap between the first and the second energy levels is huge, and then the second and the third level, it has gotten down a little bit. Okay, now from the third to fourth level, it has gone down even further. There is a very little gap, and as we go further up in the energy levels, the gap decreases and decreases. Okay, so if n is close to infinity, there will be almost no gaps. The energy levels will coincide with each other. That is, there will be no quantized energy levels, continuous energy levels. That is what Rutherford said. So we can say, if n is very large, our quantized case becomes equals to the classical case, where there was no quantization rule applied. Okay, now what are these quantized states? Why I am so much possessed with these quantized states? The thing is that the energy will be having either any of these given energies in first, second, third or fourth, any orbits. You will not be having any electron having an energy, say negative 10 electron volt. It's not possible. It needs to be either here at minus 13.6 or here at minus 3.4. Nothing in between is possible. That is what quantization is. Say I will give you a very simple example. Let's pipe this down to understand this quantization thing. Yeah, this enough. Say there is a staircase, stairs like this. Now you are going up. You may be here at this level, you may be here at this level, or here. Is it possible for you to be in an in-between level, say here, hanging in the air? Say I have drawn these stairs a bit too big for the human being, just to make you understand. Say, is it possible? Can you put your foot in between these stairs? No, you have to put it either here or here down. So that's the same thing with the electrons. It needs to be either here or anywhere, not in between in any places. So that's the thing about quantization. And as we saw, the higher energy level it gets, the levels get so crowded that there is almost no gap in between. If I can draw it like this, these are almost quantized. So same thing here, if the stairs get smaller and smaller and smaller, how will it look? Say we have smaller stairs right now, and I am making it even smaller. See, because the steps are too small, you cannot almost see any kind of steps. This looks like a continuous ramp, okay, or an inclined plane. There is no steps. Same thing happens here. The states gets continuous. Okay, it's just like the classical case that Rutherford said. Okay, so why I told this elaborately, because there may be possible question that show that if we consider higher energy level, the quantized case goes back to the classical case or something like that. So you need to simply draw this figure diagram, and then talk about that thing that I have said elaborately now. So that's for now, and now we'll see the spectrum. Okay, so that's later, we'll do it later. So that's pretty much all for now. Bye.